Discovery is the process of figuring out who your neighbors are and who your neighbors know. And it's not as easy as it sounds. Um, the the way that we find out who our neighbors are is actually pretty simple. Now, for the purposes of this discussion, we're going to ignore all the semantic compression and all the other things that Frognet gives you, and we're going to focus only on the principles behind uh, land-based discovery and land-based routing. So this is not a dive into how Frognet does this thing. This is a dive into how discovery works from a conceptual point of view. It's actually applied this way too, but it has a whole bunch of Frognet stuff on top of it. So if you think about uh, a network, you have a number of ways to think about it. The way I like to think about it is from the point of view of a member of the network. So in my case, that means somebody who is a Frognet host uh, inside a and connected to other Frognet hosts inside a network. So I have children that are attached to me through the ETH0 port. These are the laptops and the phones and things like that of my users, and I have peer uh, peer uh, networks that I'm attached to, and further distant networks. And that's an important distinction, right? Is what is directly attached to me, both to my Ethernet and to my WLAN 0 and WLAN 1 ports, uh, and what is further away attached to me. Because the way the routing works, I can get to a I can get to a distant address through any number of different different methods, right? You can think of routing like I all I can think of is the old Family Circus cartoons where they had a little kid that Dottie, you could see him walking all the way around the neighborhood, or the cat, something like that, up onto this, around that, over that, through there, through that. That's kind of what routing is. In an ideal world, you find an efficient way to get from point A to point B, but you have to let the computer know what that way is. So I know that's a little complicated, but what we do in Frognet, there are three questions that every Frognet answers. So here's the problem. I'm sitting here on the Frognet. I need to establish a map of all of the entire network around me, the entire topology around me. What tools do I have? The main tool that I have is the Apache web server and the ability to issue requests to other machines across the network. Okay. With that, I can ask them who they are and I can ask them who they know. But the question is, how do I find them? How do I start? And the answer to that is with my own direct connections. So I start with WLAN 0, WLAN 1, and ETH 0. On ETH 0, I can look at anything that is allocated a DHCP lease, right? On the machine, there is /var/lib/miscellaneous /DHCP under leases, and that lists all of the DHCP leases that a machine has or is sponsoring. And uh, if one of those is a Frognet, then I can figure that out and I can route to that, right? So now I've got a Frognet to Frognet routing. If it's up through WLAN 0 or WLAN 1, I can do the same thing. It's just that the rules are slightly different. The way that I find out who the Frognet is on the other side of that connection is a little bit different. But basically, the idea is that I can figure that out. So I can have an arbitrary number of frognets attached to my ETH0 interfaces and one each attached to my upstream interfaces. I could also have, and we'll get into this a little bit, an internet connection on one of my upstream interfaces. Now, when we are talking about discovery, then we look at first what are the machines that are directly attached to us, and we ask all of them, "Who are you?" That gives us a way that we now have, instead of just us, we now have potentially two, three, maybe more connections to other networks, and we can put those into our host table. So we can say the connection from Seattle 5 to Seattle 3 is via this TCP/IP link, right? And that's how we can set that up. So we can say that to get to here, we go through this interface, and that's a route. We say IP route add, and we the to destination, and then how we're going to get there, right? And that was the tricky part, figuring out how to put in the how we're going to get there stuff. Uh, but we did that, right, and it works. And when you do that, and you say, now I have a way to get to my immediate neighbors, you need to do that twice more, to ask them who they know, and to ask the grandchildren basically who they know. And as you bring that information back into yourself, you coalesce it, and you sort it, and you figure it out, and you say, okay, I have, three different ways to get to this address and three different ways to get to that address. Some of these routes are going to be circular, they're going to come back through me, and some of them are going to be very long. I need to choose the best route, and so that's what it does next, right? So it's easiest, I think, if we just look at the way that this actually happens. The process is initiated by a program, not a, well, it's a Python thing called run merge. Now, if we look at a machine, so this is the machine that we're on right now. This is called Seattle 3. And on Seattle 3, I have an Ethernet port. So this is a real Ethernet port. I'm sorry, this is New York 1. So I have an Ethernet port in New York 1, and that is serving the 10.102.60.1 network. That is my network, right, in New York. I also have an ETH1 on it, which is a dongle, a USB to Ethernet dongle, and that is in lieu of one of the upstream ports, WLAN 1. And this is going to their internet, right? So my ETH1 port up there goes to the internet. And then I have a WLAN 0 port that's down. It's not connected to anything right now. And then I've got these WGs are WireGuard ports. So these are transit tunnels through the broker. Okay. So this is a typical machine hardware setup with broker, and the routing table you can see from here sends me to some machines through the WireGuard tunnels. Yeah, okay, and on this one, everything's through the WireGuard tunnels except uh, the Ethernet connection. This machine is Seattle 5, and as you can see, this machine has ETH0. There's WireGuard, so this is kind of the opposite of that one. It's mostly got WireGuard stuff on it. But this machine is Seattle 6, and this is buried inside. This is a child of Seattle 5. If we look at Seattle 5 here, we can do a cat of etc. DNS, sorry, my bad, var live miscellaneous DNS mask leases, and we can see I've got it 221 there, a FrogNet host. And so if I come here to 160 and do an IPA, we can see that my WLAN 1 here is on 10.250, 250, 221. So this is that, right? These are the so if you look at the IP route here on Seattle 5 to Seattle 6, which is 160, you can see it goes through 10.250.250.221. You'll also note that we have 10.20.20 going through that same address. And the reason for that is that on Seattle 6, if I look at var live miscellaneous DNS mass leases, I've got 10.160.160.47. And if I curl that, 10.160.160.47 and ask for its FrogNet echo, it's Seattle 2. So Seattle, and its IP address is 120.120. So the Seattle 2 IP address here, 120.120, is reachable through 211 because that is Seattle 6. So I get to Seattle 2 through Seattle 6. That's what this routing table is telling me. And we do that for everything. We do not establish any routes greater than the next hop. Okay, don't ever do that. That's a bad thing. The other thing you'll note here is that I will have in some cases multiple routes to an IP address. In this case, 10.102.60.0. I'm going to reach it through both WireGuard 0 and WireGuard 1, but the link source is the same. One is a metric 22 and one is a metric 100. The one at metric 22 is the one that resolved with the lowest round trip time. So both of these resolved as valid routes to get to that address, but when they did the resolution, we picked the one with the lowest time. So run merge is how we do a merge, and it starts out going to the immediate neighbors. Looking at the upstream, downstream that we already have, and asking them who they know. It's building a list, right? It doesn't go out and do all these probes all at once. It builds a list, and then it does some work on the list, and then it sets up the probe set and goes out and does what it needs to do, and then it comes back and brings the information back together again. And it does it in waves. So it does that wave for the first one, and then another wave for the second, the grandchildren, and then a third wave for the grandchildren, I guess. And it does this as many times as it needs to until it makes a pass wherein it did not change anything. So it's going out and it's finding these routes and it's resolving all these names and everything. And if it's exactly the same as it was last time, great, we keep it that way. But if it had to change something, if we dropped off or if somebody else came in, if anything like that happened, then we made a change, and we need to do this until we don't see any changes, because that means the network has quiesced again. Now that implied, I think, but maybe did not specifically state it, but every discovery process is clean. Every discovery process starts out brand new. And we don't retain any history. We don't try to, vouch for anything that was there before. We start out again and we say, who are you? Who do you know? What are you doing? And we bring them back together again that way. Normally, you would say that that would interrupt all the traffic, right? And you're right, it would, except that we're using the .2 network for that instead of the .1 network. On every FrogNet, we reserve both the .1 and the .2 addresses of the network, And the reason we do that is that traffic flows on dot one, but discovery flows on dot two. So if you look at the screen right now, you can see a number of like 10.250.250.2 slash 32 and 10.199.199.1 slash 32, right? You know what that means. That's a 32 CIDR means it's one address. So we do discovery to one address, and then we open up to the WAC 24 once we've proven that that discovery route exists. At the end of the run merge process, we do something else. Now, during the merge, we have two transient databases involved here, two forms of FrogNet memory. One of them is the database we call the control database, and that one is deterministically defined as the machine with the highest IP address. Period. It's easy. The second one and others like it are ones that are elected. They are determined based on data in the control database that describes what the various machines are. So the machines, any FrogNet that's coming up, when it comes up, as it's coming up, it records its own state into the FrogNet shared memory space. It doesn't need to send it to a server. It doesn't need to create a message or anything like that. It just writes its current state, its current capability set into the control database. At the end of the merge process, we have the list of networked machines. We have the RTTs to them, and then we can go to the shared memory space, and we can say, give us the machine capabilities of all these machines, and we will evaluate those with respect to the requirements for being a database host or a media host or something like that. And that is what allows us to have the deterministic but floating database host and the deterministic but floating media host. And you can apply all kinds of different rules for them. For example, the media host rule says that the preferred media host is going to be local to this LAN, not something global to the entire pond, but just local to this one network. And it whereas the database host for that same thing is a machine that has big disks and lots of network, lots of connections, things like that. Those are all definitions you can make for the requirements for the services that are part of the overall definition of what a frognet is and what a frognet service is. And that's how we determine what the various hosts are and where they go. And you do that. The reason we do that from scratch every time is because we don't know. We could have separated or we could be merging, and whatever the reason is that we were called, we have to figure that out and deal with the new reality. And it's easier to deal with the new reality if you don't have to deal with the old reality at the same time. So it's taking its time doing this merge, which is kind of good, I think. Uh, Sometimes it takes longer than others. Uh, it really kind of just depends on what's going on the system. But it should be done with this in just a second. And when it does, yeah, I think that, yeah, I think it's getting done. It's a little hard to see sometimes, uh, but you get used to looking at the log, and what you notice are shape changes in the log. All the stuff scrolls by, and you kind of notice that's what it's supposed to look like at this point, and then all of a sudden something weird flies by, and you notice the shape change. So it's doing the merge right now. I just want to get that out there in front of you that the merge process is really a wave process wherein we ask our neighbors who they know and we ask their neighbors who they know, and as we do that we build the map. Now we can you can ping down a specific interface and ask it to resolve an address for you. So that's how we figure out whether which interfaces lead to what addresses, and get the round trip times for them. So I'm going to go ahead and cut this video now, even though merge hasn't quite completed yet. One thing I will do, I think, before I cut it, I'm going to SSH into the machine and show you something. So 160.161, and if we look at our routing table here now, you see it's nominal, right? And everything on it looks pretty good. So that means we're probably very close to being done here. We can cat our etc. host table, and we can see that, yeah, okay, so we're done over here now. So we can see it's got all the domains in it, and it's got the .1 and the .2 addresses in them, right? I can remove this table. I mean, hang on. There. I just removed the host table and the resolve.conf table, and the thing is still going out and working. It's doing a new discovery right now, and when it gets done with that, it will have put back the host table and the resolve.conf. Right now they're gone. Say no such file or directory, and but it's doing the active merge right here. When it gets to a certain point, which I recognize, it will have written the new tables. Sometimes you can see it in etc. Sentinels. Etc. Sentinels is our working directory. And in here, there might be a directory, a file named prognet hosts. There it is. Now, this may not be current, but this has the working pathways that we're on right now. And so if we look at hosts yet, it's still not there. So it hasn't gotten to the point where it's actually written the host table yet. It will get there very soon. But what it's doing is pinging around the network on the .2 backplane using. Oh yeah, that's the other thing. When we connect from point A to point B, we're using the regular old IP addresses for doing this, but we have a special way of getting our frognets to talk to each other that we will go into in another deep dive. But it's got to be here pretty soon. This machine that it's on is one of the machines in the middle. Like I said, it's this machine over here. It's like that machine over there. So this is the 130 machine, and it is as such. It's got things on it both through the ETH0 port and through the WLAN 0 port. And that just reminded me, I'm on the wrong machine over here where I removed the host name. That's over here. So that's the danger of being being in a multi environment. So if I run over there, that'll run that and all this. And I'm just going to stop right here now because I think you get the point that the system automatically discovers everything that it can, and that it does it by using the HTTP server and throwing a boatload of HTTP messages all over the place. All right. Next thing we want, you're going to want to look at is like what's in semantic compression and how we can get away with sending this much stuff around the network like crazy, man. because this is it's got to be megabytes and megabytes of junk, right? And the answer is no, it doesn't have to be. So catch you later. Bye.